right, that will be in the top 3. And our first team to present is GSTU. Can we get a round of applause for GSTU? Can GSTU raise their hands? Hi, could you guys come on stage? You don't need to bring your laptop unless you have presentation or notes on it. We have your GitHub repository here for any presentation material that you might need.
Can you just say we're calling them in no particular order?
I already said that. So you guys will have 10 minutes, right? Afterwards, we will open the mic to the professors and the students to ask questions. Okay? Who is presenting first, or? Good. You're free to use this laptop and do whatever you like. Okay? Oops.
So all your repos are open here? So you just, whichever order you want to go. Floor is yours?
Can I, what exactly do I talk about? What did you use? What models did you use? What did you solve? So do you have any presentation material ready for this to go?
We don't actually have, let's just see, like this is probably, you're free to just
talk about your solutions, right? Without, it doesn't have to be a full 10 minutes. Just what you did. What was the core? What was the learning outcome? What did you do? What was your model for each of the 2 days? Something simple. We're not expecting a full.
Yeah, don't worry.
Don't worry. And this is not marked.
And is it okay if we cannot like answer the professor's questions?
That's okay.
Yeah.
Your learning opportunity for you. Hello? Hello? All right.
Yep.
Good.
Hey, hello everyone. I am Mason Hu. Our team name is GSTU, and it's the reverse of UTSG. Just it's a fun fact. So I guess I'll just start talking about my part, which is the traffic science. Basically, I think, alright, just open this. I basically trained a pretty simple convolutional neural network in PyTorch, and libraries I use are these PIL, Torch Vision Pandas, and then the model is here. It's pretty simple. It's just there are 3 convolutional layers. Each layer there's the first layer there's which just corresponds to the input image, and then the second layer there's there are 62 channels. The third layer there's 128 channels. And basically this is the fully connected layer, and then yeah, there's 2 fully connected layers. And then I also use dropout to kind of alleviate overfitting of the neural network. And yeah, that's basically it. And I used the training script I used is just this. Basically, it's like 10 or like 30 epochs, and pretty like standard image recognition, like multi-class recognition training scripts. And this is probably like, it's probably like the important part, which is not outlined in my setup.md. This is the basically the ensemble.py. Basically, I use three models and kind of use the major vote procedure to like basically if there's consensus between 3 models, we just choose like we just output the output of 3 models, and if there's 2 models that agree on one and the others don't agree, just choose the output of the 2 models. And yeah, I wasn't that ready for this whole thing. And this is my data set. You can just take a look. It's the test data set, and then this is the training data set, I think. I kind of, yeah, we basically used the CSVs like pretty thoroughly. We used the bounding boxes, so there's no need for like a YOLO algorithm either. And this is what I resized the images to. And I think, yeah, that's basically it, really. All right.
Yeah, I'm just going to talk a little bit. So for the, how to go back? Oh yeah, I see. For here, so we actually have two models submitted, and I'm going to talk about the second model because I'm more confident about that because we are all from UTSG, and I actually never have using Python to make data analysis before. So I always use RStudio, and this is my first time using Python, and I just learned all the code straight from the resource hub, and shout out to all the resources that DS3 provided, and yeah, it is good. Like I watched through many videos. Yeah. And like also my first time using like the NumPy and Pandas, and it is quite interesting, like much smarter than R. Like R might be the oldest like the programming language to me, but I like it anyways. And so we first just like import the normal stuff, NumPy and Pandas, but I don't think I use NumPy for this whole thing. I just import because I saw that the people on the YouTube doing that. And we also import from like the train test split and the random forest classifier in order to process the following things. So first, like you read the train set and the test set, and then I split the X and Y from the train set and simply define the random forest classifier. So unlike Mason, like he wrote all the code by himself, but I just use someone else's function because I'm not that deep into Python, but I will learn it anyways. And then we use the random forest classifier to fix the whole function. Yeah, and then guess what? Yeah, you have the test predicted and drop the ID column, so you can put the test data whole into the random forest classifier, and then boom, you have the submission file. Yeah, pretty cool. Okay. Thank you.
Hi guys, so my name is Helen. I'm one of the teammates of GSTU. So I'm in charge of the heart disease demos. So basically I'm doing the same as Penny. I'm just like using the resource hubs. And first, in this part I'm just imported, just such as NumPy. So basically my algorithm for heart disease is logistic regression. And so this part is just like downloading the dataset and also the train the head. And then I did some like box plot to do some like data visualization, but it did nothing.
Yeah, it is actually a really good whole notebook she wrote, but the picture didn't
Shown up.
Yeah, it didn't appear. It's okay.
Yeah, and then I'm trying to, cause I found out the logistic regression is not able to do for the categorical variables. I'm trying to use one-hot encoder to convert all the categorical variables into binary, and then it's pretty simple. I'm just using the coded in the resource hub, and then we have like prediction and submission to CSV. I think that's all of my coded.
thank you so much.
Thank you.
So that was Team GSTU, TSG. A couple things. Do you guys have questions for them? Any questions? No questions? Professors, any questions for them? No? A couple points. Dropouts. There is on the YouTube, DS3 YouTube channel, I've done a research paper on dropout. The video is there. So if you're interested in what dropout actually is, please go take a look. A big shout out to Professor Shiryer Shams for having the Random Forest video on the Resource Hub. So.
But that was in our studio, not in my.
Oh, okay. But we still have Random Forest if you want to take a look. In our studio, R is an okay language, okay? R is good.
Yeah, it is good. I love it. I love it.
That did not sound.
I step our studio all the time.
Okay, sure. Okay, so we're just gonna set up for the next team.
Just give me a moment. Just set up. Yeah.
All right, just a couple minutes to set that up.
Because they don't have the.
You got both?
Yeah, I got both of us. What was it? This is Trevor. This is Celestial. I'll pin it. This one.
Okay. So the next team that will be presenting is Team GDSC. We have your Jupyter notebooks open over here, and also your heart disease as requested.
Okay.
Who will be taking the lead?
The heart disease there, celestial and traffic scientist.
You want to go for it? Okay, I can go first. Yeah. Okay,
Mine?
go first, yeah.
Here you go, sir.
I'll slide it.
You have 10 minutes.
Can I use the podium mic? All right. Can you guys hear me?
Yep. Hold on. Just need to
No, you
send.
can. That's sad.
Where's the projector?
One.
I think they can.
Okay, nice. I'm gonna start with traffic
Wait.
signs.
Give us a minute. It seems the visuals are messed up.
I think it's.
Don't worry.
Oh, is it connected?
It's not showing up now.
Aye.
No. Wait.
Debugging.
Yo, don't spam it. It's not working.
You wanna try projector 2?
No, projector
No,
is
this
gonna.
laptop HDMI should show up here first.
Are you calling teams in order of the private leaderboard?
Nope.
It is randomized. Try it again.
I can bring my laptop.
Nope.
Oh wait.
Okay, should be good.
Send to laptop. Send to projector 1.
Oh yes.
Okay, perfect.
Right, I hope you guys are excited for it because I am. I'm going to talk about traffic signs first because somehow we got 99.2% last night and we were curious. I'm just going to explain it for everyone right now. The basic idea we followed was almost similar to everyone, having a bunch of CNNs. One thing we did was a bunch of data augmentation. Yes, these are not generated by me. As you can guess, who has generated this? But I use my knowledge to understand how I can, change this stuff around to make it more appealing to our scenario. Like if you have a traffic sign, you don't want to rotate it by 90 degrees because it could become another sign. So you might want to just rotate it by 25 degrees. Oh, you are zooming out?
Yep.
Okay. Nice. So for example, the degree you want to rotate should not be that much high because it will change the sign, but you can do as much as color and brightness change as you need. After you do these much of transforms, you'll end up creating your data set, and PyTorch has this nice image folder class that allows you to easily get your data set going, and then you say, okay, it's time for me to create my model. We had 3 versions. The first version was not bad, but the second version was a bit longer, and the version that we finally submitted was V3, which ended up going from 16 channels in the first layer to 512. And each time, after 2 layers, we had batch norm, we had max pooling, and in the end, we ended up with 512 by 4 by 4 vector, which then got to 43 with a couple linear layers. Now, this works surprisingly well if you have 10 epochs, if you have 0.001 for your learning rate, and you actually write the training script, which takes a bit of time, and it will get to be training, and you end up with like 97.5%. Now you're asking me, well, how did you get 99? And then why did it got disqualified? So what I want to talk about is an important thing in machine learning called error analysis. And that is, you go through your predictions for the test set, and you want to understand, why am I not doing well on some of them? Why is this model lacking some data points? What's happening? So you make predictions, you get your predictions, you might even submit it on Kaggle and get a nice number. But then you want to not neglect the probabilities. I'm saying this is a stop sign, but how certain I am? Am I certain 90%, or am I certain just 10%? So you get all the probabilities and sort them here, and then you realize there are a bunch of 20%, 30% probabilities. They're pretty low, but you're still considering them because there's no other option. So you might assume that, well, there's something fishy with those images. So let me just go and check them out. And after you check them out, you realize that your model's labels are wrong. And that's how you realize, oh, these are the images I'm doing bad on because the model is not confident. So what can I do? Well, a normal human will try to do more augmentation, try to reach there. But last night I thought of, okay, I'm just going to label them and add them to train data. And I did it. I labeled for 1 hour about 60 images, and I added back to train data. And the model got trained on the new data. That's part of the test data. And then it improved. It got 99.2. I was happy. And the morning I wake up and they get disqualified, which makes sense, right? Because you shouldn't do that. And what I do want to talk about, what insight I got is, when you're fine-tuning it on those 60 images, you have to decrease the learning rate to pretty low. Otherwise, it will distort all the weights and you will not end up improving. And this is just a lesson I learned. And after you do the small learning adjustment and you save the model, you roll load it, and you go through those bunch of small images, you end up with a model that gives you around 99.2%. And that's all I did for traffic sign. Now my friend's going to talk about celestial labeling, and then we go to heart disease.
Wait, celestial labeling is first one. No, this is heart.
Oh, celestial is the last one.
Oh, this is traffic signs. Okay, it was the one. Yeah, final work. That's my file. Okay. Okay. More?
That's about right.
Okay, I'll start from here. Final work. This is the file name. This is for a reason because I had around 9 iteration of files, trying a bunch of stuff. Okay. So what is the general idea here? The general idea in this whole labeling was to use some machine learning model which is already trained / pre-trained, then add some boosters on it, and then predict something. But out of the 20 options that I had to choose my model, some were working fine for everything, some were not working fine for anything, some were working fine for very specific of the 3 classes that I had to predict. And then, yeah, there were a bunch of combinations there. So at the very end, after running them, after trying all possible combinations, I ended up using just 2 because otherwise it was just overfitting the data, which was the random forest classifier and XGBoost using the k-means, clustering on the XGBoost. Okay, so just going through the file here right now. I'm just reading the data here, encoding it directly to numbers for obvious reasons. Following that, there are a bunch of ways I can. I'm running out of time. But following that, there are a bunch of ways I can sort of clean the data, remove all the outliers. This is one of, I guess, the most prominent ones, local outlier factor. This checks out the outliers in the data set and sort of removes them. Following that, I realized, and this is not just like, this is on the 8th line here, but this technically is on like 108 line on the total piece of code, because this came after a lot of iterations. These are the columns that I removed because after a grid scale compilation, I realized these ones don't really matter because of the sheer amount of change in the numerical numbers they are having. ID obviously doesn't matter, but I thought at least alpha or delta will matter, but they didn't. Okay. Following that, this is just normal encoding for the XGBoost. Balancing the data, this is one of the things that I was not doing earlier, which I did later. What this means is some data points are like here, some data points are like here. But when we take a global perspective of both these data points, it becomes very difficult, and this will affect the machine learning much more than all of these combined. So we need to sort of like balance it out. How much time? Okay, yeah. We need to sort of balance them out. This is what the SMAOTE is doing. Following that is just a bunch of feature scaling. I'm using clustering for the XGBoost and normal sampling for the random forest because that doesn't need anything. This is very important. What I realized at the very end, apparently for some reason, which I'm not going to go right now in, random forest is very good at object or classifying class 1, and then XGBoost was really good at classifying the other two classes. So what I did is I built a sequential prediction system which first goes through the random forest and then goes through the XGBoost for predicting which of the other two it is. Yeah, I don't know what error this is, but probably not when I was doing it. And then this is just doing the actual testing. Yeah, okay.
I think I'm just going to skip over the part. We're going to do the
Okay.
heart disease one. We don't have time.
All right, I know we don't have time, so I'm just going to go through heart disease quickly. This was the most challenging competition in my opinion because there's a lot of noise, and so if you're not careful with how you balance out everything, you'll end up with a prediction that might be good on the public score, and then you might not do that well on the private one. The real benefit I think I did that was really helpful, okay, I zoomed a lot, is using an ensemble model. So I think a single model might not be able to do that well, but if you have a collection of models, like 1,000 XGBoosts, then it might do much better. And the second idea I want to give you guys is the fact that how you split your data and how you start your model, which will determine by seed, could also affect the performance. That is, if you start from different seeds, you'll end up with different models, and some of them are working better. So if you do something called seed ensembling, you change the seed for splitting, you change the seed for model, and you do it 50,000 times, and just keep watching. Then you might see some golden model in the middle, and then you pick it up. And that's how you can get some good prediction. And there's a bunch of other stuff I did, like a sequential model, which didn't work that much. I did also a SGD classifier, which worked almost the same as XGBoost. And in the end, I ended up submitting the one that works the best. Oh, I have time. Okay, nice. I'm going to go more. Do you guys have any questions, by the way?
Questions? I have a few questions. Yeah. So you said moving the images from the test to train was not a good idea. What could you have done alternatively?
I think what you could do alternatively is once you see the images you're doing bad on, for example, you see a stop sign that's white because the brightness is so high, you'll end up doing those augmentations on your train data. You'll go say, okay, in my train data, I'm going to do a really high brightness on these classes of images, and then you add them back to your train. And this way you don't create the biases that you mentioned, which I appreciate it. And at the same time, you get the benefits coming out from having specifically tackle the problems the model has. And just something I want to mention quickly is, other than that, I did the opposite as well this noon, and that is I got the predictions that were 100%, 99.99, and there were 10,000 images out of those 12,000 we had to predict that had these high percentage probabilities. And I got those and fed them back to the model. The model's prediction itself became a training data. And surprisingly, this led to 1.2% improvement over our original version 3, which also shows even though the model knew how to predict them, having them as the training data enabled it to go one step further than it was. I think that's maybe the benefit of also humans taking quizzes. You know the quiz, hopefully, and then you take it and you become better at the subject. So maybe these two insights will help you out in other calcul competitions.
Yes, one question over here.
You mentioned you saw something false that was in the training set.
I'm sorry?
You mentioned there's fishy images in the training set. Do you mind sharing what example because I also found some fishy images.
One fishy image I found is, if you remember, there was a sign like this, and that had two bumps. And sometimes that bump is not white, sometimes it's yellow. So the colors could change. And so in the test data, some of the color changes were not really captured well by the model. So that was one of the things I noticed. The other one was, as I said, some of the signs that were too bright had lost their colors, and it was kind of distorted. And there were some images that even I, as a human, couldn't classify. So I think, overall, I guess the human level performance, if some human just labels 12,000 images, is 99.5%. I think we got pretty close to it in this competition. Oh, yeah. You have a question?
Yeah, how did you combine different models?
Oh, that's a pretty good question. I should have gone through it.
How did you find the strengths of each one?
There are usually two ways that you can combine the predictions. One of them is called soft choice, and that is you just say, okay, we have 100 models. Which is the majority vote? 80 of them say, yes, let's go for class 2, so you take the majority one. The hard version is you get the probabilities, and then you say, okay, I know you guys want to do a majority vote, but I'm going to weigh it based on your probability. So if you have one single model saying, I'm 100% sure you valued more than a model saying, 10%, maybe, maybe not. And that's the hard version. And I think, soft version in this scenario, because hard version is too technical. But I think overall, the benefit of ensembling comes from the fact of viewing data from different angles, not just sticking to one, which will help you generalize better to the test data.
Any more questions? No? Big round of applause. All right, so a couple things I learned from this is, one thing I'd like to mention. Increasing and randomizing your seeds and all of that happens after you've hit that threshold. It's for that extra 0.1% accuracy. It's for that extra 0.8% accuracy. It's not really a good idea to start randomizing your seeds when you don't have a good baseline setup. Okay? So that's something you should keep in mind. Don't just be like, 80%, maybe I change the seed, becomes 95. That's unlikely. Okay? One thing that's, another thing that I realized from this was, I haven't actually gone through and made code, but I don't think, has anyone here tried image segmentation for the traffic signs? No? Because of that particular issue, I was thinking a possible approach would be to segment the images into shapes, and then you could make that particular part black and white and just identify a sequence of shapes in the traffic sign. After that, you could add the colors back and handle colors based on each individual segment. That might help classify things better.
What I and Arthur were thinking the other day was something on similar grounds. So we have a point of interest for the images, and our idea was, rather than training the image on the whole thing, we'll crop the image on that spot and then train it on just that. Sure. So in that sense, the model does not have to learn the ROI values. Mm-hmm. It's just because we know we can scale the grid and then cut it down, mm-hmm. and then just make it learn on that, and then on top of that we can add your values to it.
Sure. You can have a model that predicts regions of interests.
Or we have regions of interest.
Or like particular segments within traffic signs that are unique. And you can do that first, and then you can use that as your classifier. Yeah. That also works. Okay, are we good to go for team number 3?
Yep.
Okay, the last team to present, who's in contention for the award, is Team Cobra. closest to your mic, sir. And once you start speaking, you'll have 10 minutes.
Something like that?
Yep.
Great.
Alright. So you can use this laptop. This is traffic science, celestial legal, and hard disk.
Good，嚟講 CPM 啊。
You have 10 minutes.
你講咗呢個先，跟住我講我嗰個，再講 heart disease。
OK，即係我講晒呢個，定係一齊講？
我講先啦，我講先啦嘛。show 嗰個呢個。
係。
testing。
呢個係咪？係咪？
testing. So we're talking about the traffic science first, and yeah, and then like we first load the data, and then we just use like a simple split to split like a path data for like training and a path for validation, and after. And yeah, we are using like stratified k-fold to do validation on data, and then we use one-hot encoding to turn like the categorical data into like zero and ones. So yeah, and here we build like a CNN model with 2 layers here, as you can see, and then after that. We do the dropout rate here, and then yeah, and then here we are like we do the image augmentation here. So this is like nothing special, but something like. We try out like the data we try out, and then yeah, and then we feed the data. Yeah, and then we feed the data here, and yeah, the prediction happens here, and
validation.
Yeah, and then we validate the score here. And then we do the testing here, and then the prediction is here. And yeah, so that's all. We just use like a CNN model to do of this, yeah, for like traffic science.
Yeah, and the main reason like why we are using like the CNN is because like we used to try with some larger models like YOLO, but like we find out that like it's kind of overfit easily because like the image size is just too small. That's why we switched to the CNN architecture later.
Yeah, so as we just mentioned, we tried using YOLO, but because like the model is like really complicated, so it gets like overfit, and we get like the accuracy we get on Kaggle was something like 94%, but we can't like push that up further because the overfitting is like so serious. It's so serious that like on the 3rd or 4th epoch, like we are training, it's already hitting like 99.9% like the validation accuracy. So yeah.
跟住講呢個。
Yeah, so the first thing I did is like to clean the data, and yeah, and then because for this data set there's like a row with like really extreme data, yeah, that's why so this is like the really extreme data you see like the number here. That's why we need to clean this, and then because in this data like there are many columns which doesn't really affect like the prediction. That's why I chose to like drop those, and so these are some of them. And rerun ID is just like because like the rerun ID for like every single row is like the same, so we really don't need that. Yeah, and yeah, and then I clean both the training and the testing data and yeah, and we of course use cross validation with this stratify k-fold as well, like same as like the CV one, and actually we built like 7 models for this. Like the first one is decision tree, and actually in this objective function here what we are doing is we run like many epochs, like many epochs, many trials on that in order to tune the hyperparameters. So these are like the hyperparameters of that specific model, the decision tree classifier that we want to like tune. So we run like for many epochs to train those hyperparameters to make sure it has like the best validation accuracy and stuff, yeah. And the same goes for like other models. So we did gradient boosting, categorical boosting, LGBM, and like a few other boosting models, and random forest and extra trees. Yeah, we did. So
Yes, it's a bit long, so yeah, like the log is very long, so just be patient. Yeah.
yeah, so this is random forest and this is extra trees, but yeah, but normally like random forest would do better, and yeah. And yeah, this is just another boosting, and yeah, so what we are doing is we combine this model together. So we have like 7 models each. So for each of the 7 models, it will generate like a prediction file for all the test data, and then down here we are doing hard voting on like the predictions. So there are like 7 files of predictions, and we choose the best 5 models.
Yes, that's fine. Yeah, right.
唔係喎，呢個係 soft， 呢個係咪 soft？
係咪呢個？
哦，係
best 5.
Yeah, so we choose like the best 5 model here, and then just like choose the majority class, and then just display that. Yeah.
Soft voting. Yes, so like we finally come to the last part of the heart disease. Let me show you the like how we train the model. So it is pretty similar to the last one, like because they are both tabular, so the approach should be similar. So we first have some import stuff here, and we also read data and some visualization, and then we also like extract the categorical features because it would be useful in some models like CatBoost. So like we extract, and we also do another interesting stuff called feature selection, where we make use of a decision tree to help the model to identify some relevant features and remove those that are not important. So yeah, and like for the model, we also did the same like hyperparameter tuning stuff, like with the previous task. Like we have used linear model, like naive Bayes, KNN, like AdaBoost, like CatBoost, like boosting model, like and random forest, also some SVM, and finally we have even have some neural network like NLP. And after that, we try to like get the best model after the tuning. And after that, we use a really great like meta-learnings to try to combine the prediction of each of the model. Like I can show you, like, yeah, it's here. It is called stacking classifier, where like you will have multiple model inputs and the model outputs, like the prediction, will be aggregated to a meta-learning model to generate the final prediction, which helps the models to generalize well with the different point of view from different models. So this is pretty powerful, and then we just like make the prediction for that, and yeah, that's how we doing that.
Right on time too. Great. So, any questions for them? Yes.
Are you from UTSC?
We are from UTSC.
Oh, okay.
So we have another team, UTSG. I guess we can't allow more than one, so you guys have to rock, paper, scissors now. Okay, so while we're going to pull up the leaderboards, I would like to say a few things. Well, of course, a big thank you to them. So, one thing I learned here, and I've been seeing throughout these top 3 presentations, is generating and training multiple models and doing somewhat of a democratic vote seems to be an interesting approach to improving accuracy. What is the statistical validation behind this? Does having multiple approaches and then taking the, let's say, average, reduce the variance of, between the true classifier and the assigned classifier? That might be something to look into. One thing I really want to point out is the reason why we wanted you to do this presentation. And I'll speak from my experience. Last summer I had a small stint working at a venture capital firm as a statistical consultant. They wanted me to make sure that their investment strategy was statistically sound. And I was like, okay, let me find literature on what distributions are for investment returns, and let me train a model, let me find the right parameters for their data sets, and let me do all of that. And I did all of that, and I wrote up a paper describing what a heavy-tailed distribution looks like, and what the parameters are, and how we derive the optimal parameter, and anything and everything you see in class, right? What they said was they came back to me and they said, okay, but how do we convey this to our investors? They have no clue what a Pareto distribution or a Y-chart or any of that means. So it's really important for me to emphasize that presenting your material and your findings in a manner which is accessible to people who aren't as intrigued or as fluent in data science as you guys is. All right? So, by the way, it's 8 o'clock, so the individual private scores for each of the 3 competitions are now live, and the combined scores have been computed, so you guys will be able to see what it's up to. I'll be handing over the mic to Aniki or to Advi.
You sure?
Yes.
Okay.
Okay. No.
Wait.
Okay.
That is horrendous.
That's not how. Do it.
Is it not Wait, what? Okay. How is it? Leaderboard looking like?
How's the leaderboard looking like? It looks the same. It looks like a bubble. It has the same color.
Okay. Right. Yeah, that's great. How much is geek guy?
Hey, just wait 2 seconds. We're going to reveal it.
Cool. So, thank you so much for paying attention till now, and we are at the end. So I'm going to call Professor Shams, and he's going to announce the winners, but Professor Sohi will hand out their prizes. Let's go. Okay, I'm just going to take this time to thank the organizers.
here, but also for this, organizing this thing. I'll just share my experience. My undergrad was in applied statistics. I studied for 4 years. There was just one real life data set that I have seen in those entire 4 years. Like there was just one data set that I analyzed. Everything was just bookish. So this platform that you guys have and that you guys organized, I think it's an amazing platform. The works that I have seen just for the 3 group that we have seen, it's an amazing work. I was just getting awed by that amount of work that you have done. And how much time did they have?
An entire week.
An entire week. So the amount of work that I have seen, like those 3 of you, that you have done in an entire week, to me that's like 3-4 master's theses. That should take a couple of years for you to do, but you have done it in 7 days. So it's an amazing that you guys are doing, and also the organizers. So I think this is a nice platform, and anyone here, feel free to come back and then help any way possible. So once again, thank you so much for this.
Announce the prizes and this kind of certificate. Okay. So this is the winning team and these are the team members.
Teams are, do they have names?
Yes. This is very nice. You don't have a pen.
Oh, that's fine. You can just tell me the names and then I'll
Sure, sounds good.
Which one was?
Sorry. Okay.
All right, so we're just gonna announce the winner. We really didn't see the data set. We really didn't see what you submitted. We really didn't see how it was measured. So I believe you have done a great job. So if you're not the winner, please don't hate us. We're just here to announce it. Okay? So the winning team is, sorry.
Oh. I'm very sad to announce this. The winning team is GDSC.
Okay, and the team members are, what are the names? Sorry.
Alankrit.
Alankrit and
Adib
and Harmandeep.
Yep.
Okay, I don't think we need this.
Oh, I thought there was another the downtown team. I'm
Oh
my God.
You just got founded this semester.
Oh, I see.
Very nice.
Okay, yeah.
Okay, we're gonna take pictures.
How does it work? Yeah, I'm gonna give you prize, and then maybe you guys can have a certificate one by one. Yes. Yeah, actually, I want to hire you as a TA.
Oh!
Effective communicator.
Yeah.
See, guys?
And then maybe
TA shifts. That's great. Let's make this a weekly thing.
Yeah, let's do it.
Guys, you guys want to be a
I'm going to be participating.
Yes.
We're probably
I guess.
Okay, give me 1 second. Give me 1 second. Photo ops are very important, okay?
You just turn on.
You could have had your DSC logo there.
Oh.
It's fine. It's fine.
Okay.
We'll edit it later.
Okay. 3, 2, 1. Okay, do you want to do a silly one?
Yeah, let's do the silly one.
Ceiling one. Ceiling?
I don't know.
Let's do something fun. 3, 2, 1. Okay.
As we can.
I have one proposal, if that's okay with you.
Yep.
You all can come here and we can have one picture.
Yes, group photo.
100%.
Come on up.
Let's go.
You want to have the logo?